Good morning, one and all. Welcome to another session on data mining. This is Dr. Diana here, and we have started with Unit 2. In Unit 2, this is about association rule mining. An association rule is a pattern that has a predecessor and a consequent, and it has some measure of probability associated with it, which helps us predict the future. So that's what an association rule is. To mine association rules from existing databases, we have looked into the a priori algorithm. A priori algorithm, in the a priori principle, it states that all non-empty subsets of a frequent item set must be frequent. Or, in other words, if an item set is not frequent, then all of its supersets also will not be frequent. So, having that in mind, when we generate a lot of combinations of one item set or two item set or three item set or k item set, if one of them is not frequent, then none of its supersets will also be frequent, or none of the other combinations having that k item set will be frequent. So this principle is used for pruning the entire set of combinations for effective frequent pattern mining. So to do this, we started with an example, and this a priori means knowledge, prior knowledge is called as a priori. So when I have knowledge about a two item set, I will use that knowledge when I find three item sets. That is called as a priori. So I'm using my prior knowledge which I learnt from frequent two item sets when I'm trying to generate frequent three item sets. So this algorithm had two main steps. One is the join step and the other one is the prune step. In the join step, we construct a set of candidate items which are having all possible combinations of item sets. Be it one item set or two item set, you find out all possible combinations and list them. That is called as candidate generation or join step. And in the prune step, we look at those support values of all the candidates that are generated and check back with the database whether they are having the minimum support threshold value. So once we have item sets less than the minimum support value, they cannot be considered as frequent, so they will be eliminated. The main principle of a priori is used in candidate generation. When I'm trying to generate a candidate, make sure that all of its subsets are in the previous frequent set. Only then you will have that as a candidate which is generated. So we looked at an example for that using a set of transactions. So we derived a set of transactions from which we generated C1, which is the candidate one item set, and we calculated the support value of all the one item sets. And fortunately, all of them had satisfied the minimum support threshold. So all of the members of C1 become members of L1 or frequent one item set. Then from that we generate candidate two item set. And I generate all possible combinations. When I'm generating all possible combination, I should make sure that individual elements or in C2 are part of L1. That is the a priori principle. So I look back, because I1 to I5 are there in L1. I take in all the possible combinations in C2. Then I go for the support count check. I scan the database, find out how many transactions have I2 and I1 together, and I1 and I3 together. Likewise, I count for every possible combination and I list the support count values. Now, whichever has got a minimum support count of above 2 or above, is taken as frequent two item set. So I have L2 which is generated from C2 and which satisfies the minimum support value. Now from L2 I need to generate C3. Here is where I am going to use the a priori principle. Now when I try forming the three item set from L2, look at the first three elements of L2. It has got I1, I2, I1, I3, I1, I5. So the predecessor is going to be I1. The first predecessor in C3 will be I1, and following I1 I can have three possible combinations of I2, I3 and I5. They can be I1 followed by I2, I3, I1 followed by I2, I5, I1 followed by I3 and I5. Clear? Now these are the three possible combinations of three item sets I can generate from the first three elements of L2. In that, I should check using a priori principle if all of its subsets are available in L2. Now, what are my combinations? If I look here, I can see I1, I1, I1. And from I1, I can, with I1 as my predecessor, I can form I2, I3. This is 1, followed by I can form I1, I3, I5. Then I can form I1, I2, I5. These are the three possible combinations that I derive from the first three elements of L2. Considering this, now are all of these combinations available in L2? I should check for the combination. Now take for this example. Take the combination I1, I2, I3. What are its subsets? I1, I2, I2, I3, I1, I3. Are all of these available in L2? Yes, available. So in that case, this combination can be considered as a candidate in C2, C3. Now consider this combination I1, I3, I5. Consider that combination. You have I1, I3, I5. What are its subsets? I1, I3, I1, I5, and you have I3, I5. Are all of these available in L2? Check. I3, I5 is not available in L2. Therefore, this particular combination cannot be a part of C3. This cannot be a part of C3. So I have another combination which is I1, I2, I5. What are its subsets? I1, I2, I2, I5, I1, I5. Now, are all of these available in L2? I1, I2 is available in L2. I2, I5 is available in L2. I1, I5 is also available in L2. Therefore, this combination can be sent to C2. Is this understandable? Now, once you have this idea in mind, now I have generated C3 here. C3, this one is available and this one is available. These are the sets we can accommodate in C3. Once you get C3, you will have to check back with your database, find out the support count of these combinations in the database, and you should find out the support count. Now the support count of these two combinations comes out to 2. When the support count is minimum threshold value, we have set to 2. So because it satisfies the minimum threshold value, all of them can be promoted to L3 or frequent 3 item set. So this is the principle in a priori algorithm. What is the difficulty in a priori algorithm? The major difficulty in a priori algorithm is candidate generation. So every time I try to look at this generation process, I have to look back into the L2 combination when I am generating C3. I have to store all the L2 somewhere, pick up all the C3 somewhere, look back. So there is a lot of strenuous process going on in generating these possible combinations. Is there any method by which we can avoid generating these combinations? That's what we are going to see next. We have another algorithm for association rule mining called as FP growth algorithm. So the next algorithm which we will see is the FP growth algorithm. In the FP growth algorithm, we are going to try and generate a tree structure which is called as the frequent pattern tree. Using the tree structure, I am going to find out frequent patterns. I'll tell you how to do this. In the previous example, we saw every time we generate frequency or some combination, we scan the entire database once again to get the support value. Candidate generation is also difficult. Scanning the database multiple number of times also is difficult. So in frequent pattern growth, I am going to scan the entire database once and I am going to start constructing a tree. Once the tree construction is over, I will not look into the database once again, but from the tree structure, I can find out both frequent patterns and their support values. I'll tell you how we can generate this tree structure. Now imagine this is my FP. This is my same set of transactions which I have had earlier. So when I am trying to construct the tree, I am going to scan transaction by transaction. Each of these transactions I am going to scan, and for every transaction I am going to add some nodes inside a tree. So when I start with my tree construction, I am going to start with the null node. So for when I start, I am going to start with the null node, right? Now from the first transaction that I scan, the first thing that I scan is the transaction ID T100. This transaction has got elements I1, I2 and I5. These are my elements. Now before I start with the construction of the tree, I will form my candidate one item set. How do I form C1? What are all the C1? I1, I2, I3, I4 and I5. To this, what is the support value of I1? I1 is 6, I2 is 7, I3 is 6, I4 is 2, I5 is 2. I am going to order these into some arrangement based on their support value. So I am going to form my L1, which has got which one has got highest number of values? I2. So I2 support value is 7, I1 6, I3 6, I4 2, I5 is 2. So this is the order I will use when constructing the tree. So the order that I will use is I2, I1, I3. The order that I will use here is I2, I1, I3, I4, I5. This is the order of preference when I am constructing the tree. Now I will tell you how we construct the tree. First we start with the null node, and the transaction that I take is transaction ID 100. The list of entries in TID 100 are I1, I2 and I5. Now I have to arrange them in the order that I have shown earlier. What was the order we had? I2, I1, I3, I4, I5. This is the order. So when I am reordering this, it becomes I2, I1, I5. So this is the order in which I have to use for constructing of the tree structure. Now I have the tree structure already. To the null node, I am going to add one link to this node called as I1. I'm sorry, I2, because that's the first element in my order. I'm going to add I2 first. To that, I will add another node called I1. To this, I add another node called I5. So all the list of items which are in my first transaction, I have ordered them based on their support value, and that I have added into the tree. Now once I add them into the tree, I am going to give weightage to the links. This is going to become 1 and this is going to become 1. Okay, now this is where I am done with my first transaction. Now what is my second transaction? My second transaction has got two elements, I2 and I4. I have to first reorder them according to this order. So because I2 is already in, this is already in order, so it will be I2, I4 only. Now I am going to check with the tree and then see I2 is already connected to the null node. So I am going to have I2 as such. I am going to check for I4. Where should I add I4? Somewhere after I2 I should add. Now because I2 is already connected to that connected node, I am going to add I4. Now because I have added a new node, for the new node I am going to update this value to be 1, and the weight of this link I am going to increment by 1, so and make it 2. Clear? This happens when I scan my second transaction. Now let me go to the third transaction. When I have my third transaction, I already have the null here. To the null value, I have I2, and to I2 I have I1, and to I1 I have I5, and this weightage is 2, this is 1 and this is 1, and to I2 I have the weightage node I4, the weight of it is 1. Now what is my transaction? My transaction ID is 300 and I have the list of items I2 and I3. Now I have to reorder them because they are already in order. I don't have to worry. It is still I2, I3 only. Now I'll check back with my tree structure. I2 is already connected, but I don't have the node I3 connected to I2. So what I do is I add another link to this node I2 and then label it as I3. I'm going to mark this value as 1. I should now increment this value by 1 and make it 3. This happens with the transaction 3. Now I should go into transaction 4. When I'm adding transaction 4, I'm having the null value here. I have I2 with the value 3 here, I1, I5, and to I2 I have I4, and I also have I3 value 1. All of these are going to have values 1. Now I'm going to scan my fourth transaction. The transaction is I1, I2, I4. These are the values. Now if I try to reorder them according to their support values, I get I2, I1, I4. Now I have to add these elements to the tree structure. I2 is already there. I2 followed by I1 is also there. But to I1 there is no I4 connected. So from here I am going to add the node I4. I am going to make its support value as 1 and all its predecessor nodes I have to increment by 1. So this will become 4 and this will become 2. Is it clear here? So by the end of scanning of transaction ID 4, this will be my tree structure. Now I have to take the next transaction. What's my next transaction? Transaction ID 500. I've got elements I1, I3. If I reorder them, I can use them as I1, I3 itself because they are already in order only. But when I look into this tree structure, the first element here in this is I1. I don't have any I1 connected to my null node. So what I do is I take a branch from the null value, add I1 directly to this tree structure. Then I update its value as 1 and to that I1 I add another value called I3 and I should make it 1. This happens after transaction T500. Now what is my next transaction? My next transaction is I2, I3. I2 is already there, I3 is already there. So I can directly increment these two values by 1. So it becomes 5 here and 2 here. Clear? Now let me draw the structure once again so that it will be easier for you. I have null to which I have I2, its value is 5. To that I have I1 and I have I5. To this I have two nodes connected. One is I4, the other one is I3 if I am not wrong. Yeah. Then to I1 I have another I4 here. This one is 1, this one is 1. What are the other values? This I4 is also 1, I3 is 1, this is 2. So I have this node's link is 1, this node's link is 2, this node's link is 2. To this I also have another node I1, I3, each of them with value 1. This is at the end of transaction. This is at the end of transaction 5. Transaction 6. Next is I1, transaction ID 7 is I1, I3. Because I already have them here, I can directly increment their values by 1 and make it 2 and 2. The next transaction. The next transaction is T800. It has got I1, I2, I3 and I5. Now this has to be reordered according to support value. It is going to be I2, I1, I3 and I5. This is the order. Now I2 is already here. I already have, I1, but I don't have I3 there. So I am going to add one I3 to this here, and to that I am going to add I5 to this one, increment 1 here, make it 3, and you increment 1 here and make it 6. Okay now. Now this is my tree after considering till transaction ID 800. Now the next is transaction ID 900. What are my items here? I1, I2, I3. Now I should rearrange them into I2, I1, I3. So that if I try to insert here, I2 is already here, I1 is already here, I3 is also already here. So I just have to increment the support values. This is going to become 2, this is going to become 4, and this is going to become 7. Okay, now looking at this, I am going to check my previous tree structure. What were the L1 candidate items? We had I2, I1, I3, I4 and I5 values, and their respective support values were 7, 6, 6, 2 and 2. These were the support values. Now look at the tree structure. When I have, where is I2? I2's support structure with the tree is 7. That I can directly see from there. Now I1, I have one I1 here with the value 4, and I have another I1 here with the value 2. If I add these two numbers, I get the value I1 is 6. Where is I3? Now I should check for I3. I3 is here. Here I have one I3 with weight 2. Here I have one I3 with weight 2. And here I have one I3 with weight 2. So that all sums up to I3 support value as 6. That way, once the tree is constructed, I can calculate the support value of any item. Now imagine I want to calculate the support value of I1, I3 combination. Where do I have that combination? Here I have got I1, I3. Its support value is 2. Here I have got one more I1, I3. Its support value is 2. So totally I1, I3 support value will be 4. So instead of scanning the entire database again and again, it is sufficient if I look into the tree structure and find out what is the support value of each of these items. So I'm going to use only an FP tree for construction. And once the FP tree is constructed, I need not scan the database once again, either to calculate the support value or look into the frequent pattern. Now, when I look into this tree structure, how do I find the frequent pattern? A pattern, I said minimum support value of 2. So anywhere you see a link weight of 2, you can bring that into the tree frequent pattern tree. I have the link weight 2 here. So this entire thing can become a frequent pattern. So I have, what is the pattern there? I have the pattern I2, I1, I3 is a pattern. And I also have one any other three items. Yeah. So, and the next pattern is I2, I3. I2, I1, I2, I3 is there. I1, I2, I5 is also, we can derive it as I1, I2, I3 is also a pattern. So these two are the frequent patterns that I get from this FP tree. So instead of straining myself so much in scanning the data multiple number of times, I can get the frequent pattern by looking into the tree structure itself. So I hope you would have understood this. If not, I will be explaining this using the board so that it will be even more easier for you to understand. So with this, I'll close for today's session. Thank you, one and all. See you all in the next session. Stay home, stay safe. Thank you, all of you.